something. This meeting is being recorded. Okay, yep, that was the goal. We are going to just go ahead and get started. And I want to start off by showing you something fancy. Let's do something fancy. So once it detects the kernel, so it has kind of figured out which one I want to use, that this is related to GMPy GIS. Now I made sure that all of this code runs, but we will see what happens. Hang on, let me switch off every possible other software so that I can happily show things to you. Hang on one second. Okay, so what I have over here is a set of code that is supposed to show you. I'm going to run the code and you will see what essentially happens. I'm setting up a theme and I have set it so that all the plots are available to you immediately inside this Jupyter notebook. And so it's running. It has worked. Now you can see that this is a data set that is there. And so, that data set is kind of stored over in a library, in a link that is somewhere else in the internet. So in a way, I'm kind of showing you how you can extract data. And then if you know a little bit about the data, this is where, we will go into the nitty-gritties during the course. Over here, I'm going to quickly browse over so as not to bore you, but get to the pictures and visualizations. So essentially what I'm doing is here setting up the extent of this cross section. So this particular cross section is going to show you a cross section of a particular fault and some three-dimensional scans of different views of the model. Kind of setting up some resolution of what is called a voxel. So it's a volume-wise pixel. So it's called a voxel. And then I am kind of setting out certain orientation data to this particular path or this label. Then the surface points are separated out. Why do we need the surface points? To kind of show where the surface intersects a particular location. When you have a fault, you have to kind of indicate where the surface is going in three-dimensional space. And again, we have to create some check whether to make sure that all the surface points and orientations have been properly taken into account. So we create some hashes. And then we essentially create what is called a legend first, so that you know that what is the name of the strata that we are showing you, what is the structural feature that you are showing you. So for example, I have the fault features. There is one main fault over here, and we have just called it the main fault. I know this is not very, fancy, but, we want to keep saying things simple. Then we are going to put in the structural groups, like, for example, the stratigraphic sequence. So we have a sandstone, then a siltstone, then a shale, then another sandstone. So we have a very simple sequence, and then we have a fault. So that's all we are trying to show you. And we are also showing you the relation between the fault and the stratigraphy via a matrix where whenever it's in pink, that means that relation is false. So the stratigraphy is not it doesn't intersect another stratigraphy by itself. So both of them are pink. The fault doesn't cut itself. So the fault series along the row and along the column are pink because that fault doesn't cut itself. But it is the stratigraphic series is being cut by the fault. So that is the only thing that is green. Now, this becomes very important to understand the relation between the faults and the stratigraphy. Now, because this is not a full-blown proper geological map, this kind of information or matrix becomes very important. Then we are kind of generating some data. Again, I'm not going to go into the details of this. This is all for the course. Then I'm going to add some topography. So this is the code that essentially generates the topography. And then you should be able to see the section traces. This is again for later, but this is our geological map. So we can create a geological map where it shows us the sequence of material that is present and how the fault interacts. All right. So now you would say, where is the fault? I don't see anything. So, it takes a little bit of time to kind of get your eyes set up. We are looking at the XY axis, or X and the Y direction. The Z is in and out of the screen. Your fault plane is somewhere here. It is kind of going in like that. Okay. How do I know that? Well, I know that because if you look at the legend, that's the fault. So there is the fault over here, and there is the fault over here in the stratigraphy, and there is the fault over here. So this is a westerly dipping fault, if I may assume the top direction is to the north. Okay. And the different colors are essentially, obviously, the different stratas that are exposed. Now, obviously, this tells you that there is topographical control over here. Um, but this is not the beautiful looking geological maps we are all used to seeing, for obvious reasons, because this is a computer generated geological map where the system is kind of treating pixels, which are square blocks, as its controls. Whereas a human being or a typical professional geological map making software would give enough control to the human being to draw the lines and the planes and things like that, a little more with more control. Now, so let us look at the two-dimensional plot. So here you are, and this is the section where, recall that I did mention that the fault is westerly dipping. Again, this is the XY plane where Y is coming in and out of the screen right now. X is left to right, and obviously we are seeing the cross section, so therefore the depth section. And you can see if that is the case, then the direction towards the left of the screen is the direction to the left of the screen represents the westerly direction. Now, the really important part that I want to show you or demonstrate to you is, I hope you can see these small circles over here. So there is a series of circles, 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 and so on. So these are all drill data. Okay. And from the drill data, all we have done is that we have kind of made the software calculate the positions and then draw the individual contacts. Now, you will say that there are scenarios where things don't exactly match, like this is yellow, but this is on a blue plane. But this is again a matter of scale and resolution that is happening. And there are some limitations. So one has to accept certain limitations are going to be there. And this is the limitation. You can't get everything for free because the oil companies typically use but the softwares that costs several hundreds of thousands of dollars. And that's not so easy to kind of replicate. But this is, as for a first order, for a poor geology student, this is pretty darn good to get an idea of what is what. In fact, all of these arrows are indicating the dip direction. Okay. Now let's look at another section. Oh, by the way, Here I have not put in topography. Okay, so now I want to put in topography. So I am going to put in some topography, and there you are. So this is our same cross section that we had seen like a few moments ago. And you can see how the topography has kind of affected things. And now it makes a lot more sense why that particular yellow was on the blue. The only reason was that that was eroded. This blue on the hanging wall, sorry, on the footwall was not exposed because it has been taken out by erosion. Okay, yet we have kind of generated this kind of a model. Then what I have over here is some more. If I add, this is another view, I believe. This is a bit more zoomed in from another direction. This is actually section 3. This is not the same section as section was. This is a different section. So I'm looking at section 1, 2, 3. These are essentially the 3 different sections of the cube, if you were to have a cube as a three-dimensional view. And I haven't shown you the 3D view because that's kept for the main course, where you can interact with that 3D view and you can move it around, spin it around, look it from the inside, from the outside, and all of that fancy stuff, which is computationally more intense and it'll take a lot of time to generate. And I didn't want to spend so much time generating that. Over here, now I have superimposed topography as well with contour lines. And so now you can see the effect of that as well. And I don't know if you can see this. These are the traces of the cross-section lines. So one cross-section was this like this, another cross-section was like that, and another cross-section was like that, which I conveniently skipped in the beginning because typically it is very confusing to people. These are the different cross-section directions that I had originally planned out to apply on that particular diagram. All right. Let's see something maybe a little more simpler. Again, I'm just running that data set. Takes a little bit of time to run. In this particular case, I'm just trying to show you a fold. And so it's generating the fold. So let me show you the drill core, the raw drill data. This is the Y direction, and this is actually a slice. If you consider a cube, this is a slice sort of through the middle of the cube, where the Y plane is coming, I believe, hang on, the X plane is coming in and out of the screen. This is the Z plane and this is the Y direction on the along the length of the screen. And this is the drill course. The blue points are essentially the contact of one. Where did it go? Yes. This blue point is essentially the contact between one unit that is here and another unit that is there. Okay. And this is like we are considering the color blue for the rock that is further down. And then the red is the rock that is over here. And then there is another rock over here, but we are kind of ignoring it because this is a more idealized diagram. So now we are going to flip the direction and we are going to put in some rock colors. Okay, so you can see that the 3 rocks I have talked about, and this is how we kind of figure out that these are the contacts, because that is where the contact was intersected by the drill hole data. These triangles are indicative of which way is the sky pointing. Oftentimes we also interpret this as the dip direction or the younging direction. Okay. Now, unfortunately, the scale is kind of flipped because red is pointing at 0. That means this is 0th depth, and 3 is the highest depth. So the scale has to be like the other way around, but it really doesn't matter. This is just another view of the same thing, but again, this is the XZ plane, not the of the cube, and getting used to these three-dimensional section, these 2D cross sections of these parts of the cube takes a little bit of time, but hopefully you will start to appreciate it at some point of time as to what is happening. This is nothing fancy, but you're looking at one side of the cube where the fold layer intersects the side of the cube. So, you are kind of seeing a section parallel to the strike of the length of the beds. Again, the three-dimensional sketch is left for the main course, but this is that. Let's see. The next simpler version is, just a series of horizontal beds. Um, Again, all of this is essentially extracting data from drill core and creating these. During the course, I want to show you how you can actually take a geologic map in real life, convert it into a digital map, and then convert it into a model. Like the final version will be in GeoPy, and in the course, it is called GeoGIS. So you take a geological map, any map from any textbook, or if you have a map, you kind of digitize every layer of it, and then you put in depth information or elevation information, and then we kind of try to convert that into a sort of a three-dimensional geometry. So this is actually pretty straightforward for anybody to understand. Horizontal strata, we are looking at one edge side of the cube, another side of the cube, and so on. All right. So enough of this structural geology stuff. This is, again, happens to be my field of interest as well. Let us move to, let me see if this one particular program runs. This program gives me error sometimes. But if it works, it'd be a nice figure to show before I move on to map generation and earthquake data plotting and things like that. Okay. Too many things open, so it's probably taking a little bit more time than it should. It's doing the calculations. So yes, this particular program is rather computationally very intensive. Now, as it does the computation, does anybody have any questions regarding what I've shown so far? I would be happy to take a couple of questions as things are kind of chugging along. Well, it's done. Actually, it has worked. So I can actually show you. This is again going to be a normal fault that I'm going to show you, where you can, this is kind of obvious to all of you. One of the advantages of these particular using Visual Studio Code is you can actually copy these figures to the clipboard and put it in your report. Or you can save the file as whatever files you want to save it as to kind of put it in the report to show what's happening. And you can also expand these images to kind of, pop it out and look at it at a resolution of your choice. So there are a lot of options, and these days these IDEs have become a lot more popular. In fact, this is what we are going to use from now on. We are not going to get into Jupyter Notebook and all of that stuff. It's just no point of doing that. This is the three-dimensional model, but I think this is going to take a very long time. So actually, it has solved it for me. I have to share it again. So hang on 1 second. I will do a quick share. So this is your three-dimensional model that I was talking about. Okay. And you can play around with this as much as you want. And there are two things I want to point out to you. Obviously, it's a little choppy and it's not as smooth as what a geologist would want, but these arrows are extremely helpful indicating which way the direction towards the sky. And for a first order model, this is perfectly fine. This is fancy stuff. Okay. When I was learning geology, I never had this opportunity to kind of play around with this. And then you kind of go crazy with looking at things in all possible directions. Okay. Well, anyway. I believe you can save these ones. You can zoom in, zoom out as well. This one, I think you can save. There's a way to save it. Maybe there is, and I don't know. But from the code perspective, definitely you can. Okay. All right. Before I move on to the next thing, any questions? Somebody, is it possible to get again, Mr. Nikhil will answer that question. Let's see if we can get things going on here. So this is essentially a ternary diagram, and I'm trying to show you. These are some value. I think the data didn't get downloaded. Anyway, we can't find file. File is right there. Let me run it again. Anyway, again, we have this ternary diagram of water, air, and limestone, and we can create based on. So this is essentially plotting permittivity over here, and we can actually plot the permittivity based off of this limestone, water, and air. So it's a limestone aquifer. How much air, how much water has been calculated, and we are trying to plot that, and based off of that, kind of figuring out what are the different kinds of permittivities that are there. Let's see, what about this one? This one is by GMT. So this particular plot is kind of pretty fancy. There are many occasions where you plot 2D data like XY plot. And before you do any kind of statistical analysis, one of the fundamental questions that needs to be answered is the variable that I am plotting, is that normally distributed? Now, these kinds of plots are very handy in demonstrating to you that yes, your components are normally distributed, and now you can do some statistical analysis of this. What kind of statistical analysis? That's a completely different course on statistics that, again, you can talk to Mr. Nikhil about that. We discuss exploratory and inferential statistics based on univariate, bivariate, multivariate data sets using Python programming, of course. So you can write programs that will generate these kinds of figures, and again, you can save them, uh, you know, put it in your paper, whatever you are trying to put it in. Don't save, save. This one is plotting of earthquake data. So I have selected Japan and its associated earthquakes. So the first figure that I have plotted is essentially where, again, observe that I've kind of made a quick and dirty plot. I have not made a fancier plot. Obviously, you can make a fancier plot where obviously the latitudes and longitudes will be visible on both sides, a fancier clipping, all of that. But this is more for demonstration. And here I have just plotted the earthquakes. There is nothing other than showing spatial distribution of the earthquakes. Then I can start to make it fancier, where I can say that I believe the circle size, yeah, so the size controls the magnitude. So how big or what is the magnitude of those particular earthquakes. So it's the same position, but I'm changing the radius to kind of say the magnitude. Now, for any earthquake, obviously you want, in addition to magnitude and spatial location, you want depth. At what depth this is happening. And what I can do is then create a map of a color bar, add a color component that tells me the depth. And this is the color bar that says that violet or indigo, whatever color you want to say, is the shallower depths. And the red, pink, or the towards the hotter or warmer colors is essentially the deeper depth. And this makes complete sense to you if you are in geodynamics, that the Pacific Ocean, Pacific plate is diving underneath Japan over here. So you have the shallower earthquakes, and this is the subducting slab that extends so far away, which is obviously there is a rollback, which is why you have Japan detached from mainland of China, which this is the back arc that is there. So, uh, so that's that. Let's see a contour map, perhaps. Oh, go ahead. So the code has already run. And so I can create from the data, different uh, sort of levels of details. So the first one is kind of like the bare bones. I want to see the main, and the advantage of this over any other software, including QGIS and ArcGIS, is this ability to make index contours immediately. I'm not saying that QGIS and ArcGIS cannot do it, can do it, but over here you can immediately ask that what contour values will be your index values. And as you play around with the index value setting and the interval, you can start to get details over here. Again, I can again play around with values over here. Then essentially, put some map details like this boundary with latitude, longitude information, and then put a color based on the elevation kind of stuff. Again, the pixelation is because I didn't go into too much detail of trying to smoothen things out. So you can see the pixel values. This is the elevation color bar. Um, what else? Let's see, cross section. Maybe I don't think I ran that one. GMT. So this is like a one-shot program. Running. Where did I go? Why did it come back to ternary diagram? Looking at the cross section. Okay, so here is the cross section. So what I have over here is this area from across Japan and into China. And you can see this is bathymetry elevation. And you can sort of see that that can easily be developed. So this is the east coast of China. This is ocean basin. This is Japan. This is the Pacific plate diving underneath. So I would say this is a pretty darn good plot to kind of show things. Now, obviously, you can kind of generate many more plots where we can actually plot the Wadati-Benioff zone. If people who are interested in earthquakes, it's that tells you where the oceanic plate is going, how it is diving. So all of that you can do. Okay, so that's all I have. I want to show you for GMT. There's many other stuff, but again, I can. It's too many things to show. I want to show you one code about seismology because I have had a lot of requests earlier to show something on seismology. So here goes nothing. Open folder. Obs by this one. Where is the code? I think it's still trying to open the code. Give me a second, I'll just pull up the code. I think I put it somewhere in a different place. Okay, I think I have it. So I'll just type it out. I wrote it, I think I accidentally deleted it. So that's all right. So you get to see me type it out. Uh, read. Uh, ST. Read. Slash. This is where I'm going to make a typing mistake. So I'm just going to copy paste that. And then I'll simply say print st, run the code. So it has, so this essentially tells me that it has run that piece of code and that the data contains, this is the seismic data that is there, and that it is measured in 200 hertz. There are 36,000 samples that has been collected. And then I can figure out that this is collected as one data set. I can demonstrate that to you. I found out the length, and now I want to plot the first trace. So I'll extract the first trace. So I'll say trace equals st0. Now this means extract the first, whatever is in the first index. In Python, the zeroth index is zero is considered the first number. So that is an index. And then I can say print tr. Then it tells you that it gives you the same information. And now I can say, let us look at some of the details. Tr dot stats. Now, if I do that, it tells me um, what station number, what station, what channel. This is the Z channel, that start time and the end time of collection of this data. And then what is the sampling rate, and then some information that a seismologist would have better understanding than me. But essentially, I call it the squigglies. So the squiggly according to the and then you can extract different kinds of information. I am not going to do that now. I am just going to show you the plot. I am just going to show you the st dot plot. So it is going to plot the entire data set for that time being. And there you are. That's your data set. And this is your seismogram. And now you can do many different things with this. What? I don't know. I'm not a seismologist, but it's fun. You can do a lot of different things with this. All right. Um, all right. So this was my original plan. Like this is all I wanted to show you. Maybe a little bit of PyGMT, more of PyGMT, but it's all right. This is good enough to kind of show you the kind of things this can do. Um, if you don't hold it against me, I'm going to take another few minutes to show you the other thing that I had downloaded and prepared for you, just to see what it does. Uh, Nikhilji, do I have your permission, or do you want me to stop here? So, file, open folder, ArthPy. See, I have nothing here, so I'm going to create something. And I'm going to say arthpy1.ipynb. Okay. And I am just going to go from here. Let's see. Log 10. I'm going to port by as ET. I have to select a kernel now. Where is ArthPy? It's right there. Then I'm going to port by dot spatial as yes spatial as yes dot dot as t port raster IO as RIO. I believe that's all. Okay, now there are a few more imports. Oh, dot five plot SPLA. Okay. I found my old program. That is, let's see, V, C, okay. So these are all the libraries I have to download. See, let's see if all of this gets accepted. Requires, okay. So this is another advantage of VS Code, that you can directly um, get things. Once that installation is done, just be patient for a few more minutes. This should work out. It's just installing a few things. I'm going to even get my code ready for once it is done, I can just ask it to show the code. Again, all of this kind of might seem, you know, uh, foreign language to if you have not used programming before, but at the end, after once you take the course, you will get an idea as to what is happening. This is nothing but just another way of us communicating with the computer in a language called Python. I think the installation is done. Mm, let's see. All right, yeah, it's done. So now once it connects to the kernel, I'll just run this particular cell. Just reading all this and importing. No module name, Plotly. Number 9. Well, let's see if I don't import that, what happens then. Okay, everything else got imported. And S dot sentinel band is not defined. Ah, yes. I never down. Okay. Control C. I forgot to put that code in. Let's see. Okay, more error. Need at least one error to array to stack. Evaluate stack. Okay, that's okay. That is correct. That is correct. That is correct. Sentinel bands. The spelling is correct. That is correct. Anyway, this is what I was afraid of. There's something that I haven't looked into carefully. But again, if things had worked out, the what I could have, what you would have seen, let me show you that very quickly, that I would have grabbed some, what is it called? Um, this is some satellite imagery data. And if I may share this document, share the Word document. So this is what you would have seen uh, had I been had the code run, which is essentially the different bands uh, of the 12 bands for a piece of uh, area from satellite images. So, again, this is some new stuff that I plan on, introducing, and we are thinking about where to put it. So, Mr. Nikhil